Hi, everyone, and welcome to the MLOps Live webinar series, where we discuss how to bring data science into real business applications. My name is Sahar, and I'm the VP of Marketing at Iguazio. It's great to see so many of you here with us today. We're really excited to be hosting Nick Brown, Senior Data Scientist at IHS Markit, on this session. For those of you who are not familiar with IHS Markit, this company is a leading information provider with over 13,000 employees. It's one of the 100 largest US corporations, and Nick leads the company's data science team. Also with us today is Yaron Haviv, co-founder and CTO of Iguazio. Together, Nick and Yaron will be speaking to us about scaling NLP pipelines. Nick and his team have built an impressive NLP pipeline that makes massive amounts of PDFs searchable and indexable for the entire organization, and he's going to share from his experience today. Nick will start us off with an introduction to IHS Markit. Then he'll discuss NLP in engineering and product design. After that, he'll talk about vertical to horizontal engineering and focus on scalability. Then touch upon the pipeline building blocks, events, and serverless. And finally, discuss pipeline composition, scaling, and infrastructure. After that, Yaron will talk about the importance of adopting a production-first approach to seeing real business value with AI. He will share the 4 pillars to MLOps acceleration and finish off with a live demo. Just a moment before we get started, I'd like to invite you to join over 500 MLOps and data science practitioners on our MLOps Live community. This way you can ask us questions and continue the conversation even after the session ends. We'll drop the link in the chat box now. During the session, we'll also run 2 short polls to hear about you from your MLOps journey. So please do fill those in. These polls help us make these sessions as valuable as possible for you. And as always, we'll make sure to share the results with everyone at the end. We'll also leave time for Q&A, so feel free to ask us questions in the Q&A panel at the bottom of your screen during the presentation, and we'll do our very best to address them all at the end. We've now put everyone on mute, and we're recording the session so that we can send it to you afterwards. So without further ado, I will pass the mic over to Nick to get us started.
Thank you all so much. So as Sahar said, my name is Nick Brown. I work at IHS Markit. I'm a senior data scientist, also an MLOps architect for one of our projects. We have many data science teams, and I'm working with one of our many talented data science teams. So today we're going to be talking about NLP, as we discussed, and how we bring it into production and how we scale it. So as said before, we're going to be talking about first what IHS Markit does. We'll drill in on my specific business line, EPD, engineering and product design, and our NLP business use case, and get really comfortable with exactly what kind of problems we're trying to solve. Next, we're going to move into how we do horizontal engineering now, and how we moved away from being solely focused on our vertical scalability. From there, we'll build into exactly what we did to achieve horizontal scalability using events and serverless functions. And we'll wrap up with kind of the key challenges and how we've overcome them in the NLP pipelines from a positioning of composition, scaling, and infrastructure. So some of you may not have heard of IHS Markit yet. We affect tons of different decisions around the world all of the time, but we can be a little bit behind the scenes. So who are we? Well, first, we really combine industry expertise, technology, and data science to create value through information. Our high-level industries include the finance industry, transportation, energy. So we can answer sorts of questions like, how much oil is forecasted to come out of any well in the world, at what price, at any time. We might also be able to tell you what regulations and standards are important for a given aircraft. We have a tremendous amount of coverage around different industries, and my specific industry is in our cross industry. So engineering and product design covers both transportation and the energy sector, focusing on how we can solve the biggest problems for innovation and help our customers deliver complex projects and new projects on time and on budget. And how we do that really is a few ways. So the first thing is that we have an unparalleled content collection from patents and journals, standards, regulations. If an engineer really needs it for their day-to-day job, we have that in our content collection. On top of that, we have been doing AI for a very, very long time, multiple decades actually. So we have a lot of experience in the search space, driving sort of NLP-based extraction, enhancement, and obviously ML throughout that entire process to really enable it. And finally, we have a number of subject matter experts who not only work with our customers, but also work with our data science teams. As many of you know, it's incredibly important for a data scientist to understand the industry that they're in and to really understand what are the nuances and the unique aspects of that specific algorithm or that specific piece of subject matter expertise. So we have a great partnership between our subject matter experts and our data science teams. So with that understanding of really what IHS is doing and what my team is doing within IHS in engineering and product design, let's jump into what our NLP use case looks like. I think that it's fairly unique in the industry. So it really boils down to the fact that engineering documents are very, very complex. And on top of that, innovation as a process is deeply challenging as well. Engineers in general, they have a large amount of sort of spread out information inside of their documents. And these documents, we can think of them as PDFs, but they could also be Word documents, Excel documents. They can include things like tables and diagrams. It's not just natural language in sort of the sort of English language spoken sense either. It's all sorts of mathematical equations, scientific diagrams that are also included, and language is mixed into all of these. And so that is one of the key challenges that we have to deal with on a regular basis. And so what we're attempting to do is really encode the information that is most critical for engineering innovation into our workflows that allow an engineer to be able to find at sort of a moment's notice whatever is most relevant to the work that they're doing right now. So it's in a lot of ways it's like a search engine. It's a deeply complex problem though that we're working in. And the final piece of this is document structure is deeply important to how these documents are set up, because it's not just one continuous sort of scrolling page. As we'll see here in a moment with an example, it's very much so the semantics of the document are built into its structure. So let's go through maybe a more concrete example, something that we're all maybe a little bit more familiar with. So I actually pulled a paper off of ArchiveX, sort of an engineering style document about how using neural networks to maneuver ships. So what kind of things might we want to pull out of this document? And let's also keep in mind that these documents don't always come to us with all of the content embedded inside of them. So the first challenge a lot of times is potentially dealing with something that's just an image. So things that we might want to pull out, title, obviously very helpful, authors, but we also see down here that there's some author metadata. And this is very, very far away from where the authors are mentioned at. So not only do we need to be able to extract it, but we also need to be able to make this sort of implicit linkage between the two of them and say that this, these entities are being talked about other places in the document as well. We also want to pull out the structure again. So things like section headers become very important. We might want to have section mentions, because that can help us derive how different parts of the document are related to each other. Different entities might be related to each other. As I spoke about before, a part of engineering documents that we have to deal with constantly is the fact that there are other symbolic languages mixed in. So we need to understand what formulas are being talked about, where are they being talked about elsewhere in the document. Also figures. What do these pictures mean? Can we relate them to formulas possibly? How can we use the description to extract more information, potentially even out of the image itself? And then speaking of images, it's not uncommon for us to have actual real world images embedded into a document and to need to be able to potentially classify things that are inside of that image, look for references inside the document. We need to be able to pull out all sorts of different types of tables. And then that gets us down a whole rabbit hole about inner table dependencies, row column mentions, all sorts of structure that can allow us to drive more information to present back to our engineering end users and allow them to innovate more rapidly and find the information that they're looking for. So in summary, that's a lot to sort of take in, but I think the best way to think about this is that for a single document, we can have hundreds of different operations to apply to really extract and enrich what's going on inside of the document. And so not only is this challenging from an NLP perspective, but now we really need to think about when we're productionalizing it, we also have system engineering challenges. Considering that we have millions of documents that we need to process, and not only are they of different types, like I spoke about earlier with Excel and Microsoft Word, PDFs, but they potentially are very different in length. So we might have documents that are 10 pages long. We might have other documents that are 10,000 pages long. How do you scale and how do you handle sort of the different lengths of processing time that might need to be implemented for these different document lengths? As I spoke about earlier, you'll also notice that not only are we doing sort of this typical NLP-based process, but if we have an image, we might need to be able to do object detection on it. There are all sorts of rules-based algorithms that we put in place, in order to do some of those sort of longer-term linking inside of the document, as well as probabilistic rules and probabilistic models that we put in place. So it's not like we're just running one or two, deep NLP style models. This is a very, very wide variety of data science that we have to be able to do over these documents. And then obviously with hundreds of operations to perform, all sorts of different sort of high memory GPU-based modeling approaches, scaling hardware is very expensive, and it's something that you have to think about ahead of time, because once you get into production, this can become very cost prohibitive. And then finally, when you have all of these different types of models that you want to be able to apply, that there might be small tweaks that you want to make to them and introduce them back into the system. So there might be sort of specialized entity extractors is a good example of that. So being able to standardize the interface between those becomes paramount, so that we can simply add on to our pipelines instead of having to rebuild them from scratch at all times. Also allows data scientists to iterate and innovate themselves much more rapidly. So this really leads us to, as I spoke earlier, we've been doing this for a very, very long time. So we've had solutions in place for over a decade now. And what we've been focusing on before, so I must commend my colleagues who have been here much longer than I have. They were very focused on, and we've been very focused on, sort of that vertical performance. So how can I get the most performance for the hardware that I am currently running on? So that meant modules and packages built in C++, C#, all sorts of compiled languages, lots of profiling, again, making things more tightly coupled as a result of that to improve that vertical performance. The problem is that as we start to see, again, the big data revolution spread into these engineering companies as well, and we're needing to process not tens of thousands, hundreds of thousands, millions, tens of millions of documents, we realize that we need to move not necessarily away from vertical scaling in the sense that we no longer care about performance, but more towards horizontal scaling. So for those of you who maybe you're not as familiar, this diagram shows it pretty well. Instead of scaling the hardware up and being on a single machine still, we want to be on sort of smaller machines that we can provision very quickly and scale out our workloads. And so how do you go about doing this? And how do you go about, especially in a culture that has been very steeped in wanting to sort of tightly couple things and keep everything vertically performant? Well, we decided to focus on three different architectural concerns. So the first one is elasticity, so the ability for us to change sort of our work scale size. Evolvability, so focused on decoupling our individual components and moving towards standardized interfaces like we talked about before. And scalability, so focused on not just how much performance are we getting out of this, but how easy is it for us to add another replica of our workload, and for that replica to potentially go down and come back up. So the way that we're doing that is really by leveraging the cloud, Kubernetes, Kafka, and of course Iguazio. And our cloud of choice is, of course, the wonderful AWS. We've partnered very heavily with them, and we'll talk a little bit more about how they're really enabling some cost savings as well later on. And so with these different technologies, what really are we looking for? What are we moving towards? Well, so the first thing is, because of the issues around cost engineering, our specialization of hardware is very important. We'll talk more about this later, but the ability to run only the processes that need high memory and or GPU on those specialized pieces of hardware is paramount, so that those can be scaled down and really reduce our cost. We also want to make sure that our development and production languages are the same. So having to throw things over the wall really hampers your ability to bring new functionality online, and it also adds additional complexity to your deployment pipelines. And then we want to focus on making sure that features themselves are independently evolvable, and this is where we really use the streaming-based approach to essentially break down maybe one very small component of the pipeline, like extracting out paragraphs or an image or something like that. And then that topic or that stream becomes sort of the source of record for features. So additional components come online, they can just start reading off of that. And so this is all working up to sort of, again, the solution being for us, moving towards serverless and streaming as our sort of fundamental architectural style. And we'll talk more about how we came to Nucleo and Iguazio. I think some people might be thinking, well, why not Flink? Why not Beam? Why not ksqldb? Well, what you have to remember is that we're not in the structured data game. We are in fact, in the unstructured data, and so those systems are not as well designed for what we're looking for, and some of them also do not have that sort of merging of development and production languages as well. So with that being said, let's talk about how we achieve this with events and serverless. So the first thing, like I spoke about earlier, is that we're decoupling our pipelines, and we do that using the pub-sub pattern. So what this means is that we essentially have sort of an unlimited number of publishers, an unlimited number of subscribers on either side of a stream or a topic. And what this allows us to do is sort of not need to worry about, when you're publishing out events, who's going to be using these in the future. Really allows us to bring new machine learning components online to an existing set of functionality, and again, extend what we've already built. And that's really, again, extensibility, very, very important for our architectural style. In addition, using these topics allows us to create a stable interface between our models. So the topics or the streams themselves actually have defined schema and evolvable schema. And so that allows us to bring new functionality online while not breaking old functionality, which is obviously incredibly important. This led us to thinking about how we really needed to approach our serverless. Lots of serverless options out there, but we did have some asks that made the choice much more specific. So the first thing is we had to have support for GPU. Deep learning models, they need GPU in this day and age, and we also needed to be able to support extremely high memory at times. So it's not sufficient for us to have a memory cap on what we can use. We also needed a solution for the cold start problem. So NLP models, when you bring them online due to the high parameter set, can take a lot of time to sort of be loaded into memory. And so if you're having to do that on every event handle, that can be a problem. We also needed to be able to scale both vertically and horizontally. So being able to scale up another replica always has a cost associated with it. Some of that's the cold start problem. There are other pieces of that as well, though. And so having those sort of that vertical scalability, where even within a single replica, I can thread sort of additional requests through, very, very important for us. We also needed to have the ability to have a sort of a local cache for our documents. So some of these documents can be 0.5 gigabyte in size. Well, you really don't want to be sending that over the wire or loading that in. Being able to just sort of mount that up underneath the function as it's running really improves the performance of the pipeline. And then because of how complicated these pipelines are, we need to be able to compose them, deploy them, and manage that sort of the multi-stage aspect to them in an easy way. And that is not something that comes out of the box with a lot of serverless solutions. And so that's what led us to Nucleo. And in fact, Nucleo is really this wonderful combination of sort of a stateful, stateless function as a service. It has pluggable event sources, so we can use things like HTTP or Kafka. In certain scenarios, it can absolutely scale all the way to 0, which is wonderful from a cost savings perspective. And also our data services, like I was talking about earlier, we're able to mount underneath the function pretty much arbitrary disk space. So that becomes a lot less of a problem for us when we're needing to work on these large documents. And as far as consuming off of these topics, being a consumer of a topic in the pub/sub architecture, Nucleo supports that as a trigger type, so we don't have to think a whole lot about it. And the function replicas really take over the ability to simply subscribe and start consuming events very, very rapidly. So with that being said, sort of the building blocks of how we're tackling this pipeline, let's talk about the sort of how we go about dealing with pipeline composition, how we deal with scaling and infrastructure. Really, this is the productionalization piece. Because from a high level, NLP applications in the abstract don't really look that difficult. You sort of parse the document, you extract certain different entities and sort of basal types out of them, do some linking, maybe some vectorization, and then pass that off to a search system. Right? That's not too difficult in the abstract. In reality, the pipelines look, this is just an example of how complex they can get, and this is only one small part. So you can see this sort of directed graph where we're not only are we doing sort of rendering and extraction, we have multiple dependencies where we're streaming in sort of different parts of the pipeline into individual components. Something like named entity recognition. Component might need something from text statistics, it might need vectors, it might need part of speech tagging to be able to do its job properly. So merging streams is a very important capability when you are thinking about this, and just think about trying to manage this and how difficult that can be. So, and that's not to even put in the fact that now some of these have very, very different hardware requirements. So ones in purple here would be good examples of ones that might need GPU, ones in green, good example of sort of high memory style functions that we might need to have in place. And we need to have this independent scaling too, because what we'll find is that as documents go in with different levels of complexity and different lengths, you'll identify sort of different hotspots as time goes on. So being able to individually scale every one of these components and the infrastructure underneath it becomes incredibly important. And we also want to be able to share that infrastructure. So as a hotspot starts to go away, and let's say that hotspot is using GPUs and that starts to scale down, we want to be able to pass that off to other parts of the application of the pipeline that need that GPU at the time. And so this for us is solved for in a lot of ways by MLRun serving graph. So MLRun is this great technology that lives on top of Nucleo, does a lot of other stuff, but for now we'll talk about it as sort of an orchestration framework for these multi-stage real-time pipelines. And so what this allows us to do is define a very simple topology and subtopology even sometimes to really allow us to scale independently and also to keep from having to maintain that sort of visual picture of everything going on. It's defined in the code itself and makes traceability a lot easier as well. As I spoke about earlier, AWS is a really critical partner of ours, and something that we've worked very hard on is how we can scale with uneven load and ephemeral hardware. Because how this works is new documents come online and we essentially need all resources on deck. We need as many GPUs, as much memory as we can get. And so what we have to do is constantly balance the cost with the throughput. How we do that is by using Spot. Spot is one of these, it's basically excess capacity in the data center that allows us to really use it at a much lower cost, but it does introduce operational complexities of needing to be able to move our workloads around. Fortunately, a lot of this is solved for by using things like Nucleo, Kafka, and sort of event-style systems as the back pressure can be handled for us. And it really allows us to make a judgment call about whether or not we want to continue processing when that lower cost hardware is a bit, sort of not available, or if we want to just sort of hold off. And all of this can be done automatically behind the scenes. And the last thing I'll talk about is another thing that we've really tried to implement in our systems, which is this idea of event-driven compute. And this comes back to, as new documents are coming online, how do we make sure that we're cost engineering effectively? So let's say that we have a set of messages coming through the system that do require GPU, and then maybe very large, very expensive GPU instances. So what we're seeing here is, from the left, we have the messages coming in. We have a consumer group that's reading those messages, and they'll pass off to a Nucleo function, actually. It's really a compute pool. So when it's not in use, when there's not much throughput through the pipeline, can actually scale all the way to zero, which is an enormous amount of cost savings. As these new messages come in, the replicas scale up, the hardware scales up. We're able to do our processing, pass it back, and really, again, think of it more as an event-driven compute pipeline rather than needing to have the compute inside the consumer group itself. There is obviously a trade-off here, though, in that there is some pretty complex retry and back-off logic if the compute pool is not available due to spot outages and all that. And so we were going to need to implement that. Fortunately, ML Run comes with a remote step that allows us to do this out of the box. And so, really just to kind of summarize how these two technologies are really enabling our scaling strategy. The first thing, and one of the most important things, is really simplifying our pipeline definition. It's very difficult as pipelines become scattered across repos to keep up with this. And ML Run really allows you to sort of define all of that in one place for a subtopology, subpipeline. The elastic scaling of our resources was massively important. And again, with Nucleo, this is really something that comes out of the box. It's something that when we need it to scale to zero, it does for us, and then releases those resources, and from there they can be released back and sort of terminated, saving us a lot. And then we also have common components that we can define in ML Run. So if a person needs to come online and really use something that we've already built, there's a best practice for it, and just use configuration to change its behavior. That's pretty easy to use our internal function marketplace for that. And then function monitoring, if you're not doing monitoring right now, I will absolutely encourage you, start to get very comfortable with it. It will save you so much headache, so much time, and really being able to profile our function performance in real time is something that's been very important to us, and something that you should all consider making sure it's built into your pipelines. So in summary, we covered a lot today. So let me just kind of go over the key learnings that we had. So the first thing is that NLP pipelines are not sort of the traditional one-off. I send a feature vector to a model and I get back a singular response. NLP requires really very, very complex pipelines running many operations over the same features themselves. They end up having very complex compositional logic as time goes on, and that becomes a very high operational burden for us to keep up with. So being able to componentize even the sub-pipelines themselves becomes something that's very important. Cost engineering is something you need to be thinking about from day one. NLP is definitely one of the most expensive types of AI to get into. So if you're not thinking about that now, and you're thinking about an NLP initiative, start really defining what you think those resources are going to look like and how you're going to overcome that. For us, auto scaling over streams of NLP events has been a great way to control expenses. I would absolutely recommend that as an approach, but do know that that does come with some engineering complexity that you will need to solve for, or use a technology that has solved for it, like ML Run or Nucleo. And the last thing I'll sort of end with here before I pass it off to Yaron is that when we're thinking about scaling, I think we tend to think about just hardware, but another thing you really want to think about is how do you scale your teams? How do you scale innovation inside of your data science department? And so building out sort of common components, standardized components, really focusing on at the beginning on interfaces and things like that allows you to scale your team's productivity because they're not having to reinvent the wheel every time. Being able to pull those and use configuration to change behavior is a really way to scale how you're working. So with that, I'll say thank you to everybody. Can't wait for the Q&A, and I will pass it off to Yaron.
Thanks so much, Nick. That was really fascinating. Thanks for the deep dive. Just before Yaron starts his part, I will mention that we're going to send links to both Nucleo and MLRun in the chat right now. These are both open source frameworks that are built and maintained by Iguazio, and you can check them out. And you know, they're open source, they're on Git, and it's completely free to do so. And we're just going to take a quick poll before we dive into the next bit. So we'd like to hear from you where you are on your data science journey. We're just going to, and with that, we will move on to Yaron's part. Yaron, please.
Okay, thanks, Sar, and thanks very much, Nick. Before I dive into a demo, a little bit of an overview. Most organizations, when it comes to machine learning, are still oriented towards the research part. So you take a piece of data, you run some preparation, you build a model using regular training or using AutoML services, you evaluate, and then at a certain point you may deploy some endpoint that serves the model. That is a relatively simple approach, which is contained within the data science team. Next. Sorry. But when you really build an application, there's a lot more to it. If you're trying to build an application that generates value and interacts with business assets, with data, drive some actions that maybe index in a database or trigger activities against users, we need to build something more like what you see in the diagram. And that involves way beyond the data science team. It involves data engineering. It involves building the serving pipelines. So I'm saying serving pipelines because just as you've seen with Nick, it's not just about model serving. There's a lot to it. You need to get the document, parse the document, extract text, and do some models, maybe sometimes even more than one model, whether it's an ensemble or a composite model. And then you need to drive action and send notifications and alerts and so on. So we need to build those pipelines for production. And we also need monitoring. So there's a lot of aspects that need to be handled. And pretty much most of them are not handled by data science teams. They're handled by data engineers, software developers, DevOps people, data ops people, etc. And that really what leads to a very long deployment process to production. What we're trying to do is simplify this overall flow. Next, Sar. Essentially build a solution where there is a continuous flow of productizing your AI application. And so if we're looking into the flow, it contains 4 key components. The first thing is about processing data, whether it's structured or unstructured data, whether it's these are sort of tables or documents or images or video feeds. We need to process those and create some data set for the training and later on also for the serving and inferencing. The second piece is essentially building an automated flow for running the training and testing the trained model in some CI frameworks and finally generating a valid model that we can trust and performs and so on. The third aspect is taking that model along with live data that feeds off a stream or a database or some other source of truth, processing that, generating actions, interacting with users, and so on. So this third piece needs to interact with the model as well as with live data. And this piece also generates a lot of telemetry or production data that needs to be analyzed to identify maybe our model misbehaves. Maybe we want to measure the impact of the model on the business application. We want to see what kind of activities are generated, all that. So we need to monitor what's going on with the production pipeline. And we may write back all this information back into the feature store So later on, we can do post-analysis, like explain the behavior of our models, measure accuracy of our models, and so on. So this is the operational pipeline. And instead of looking at like the previous way, where it's all siloed, different people work on it, a lot of patches and glue logic, we want to look at it as a holistic stack where essentially things pass by pointer. There's no need for glue logic, like in the previous example. And this is really what MLRun tries to do, is orchestrate those four pieces of this evolution of machine learning application stack, starting with the feature store for feature processing, the sort of the CI flow for building those machine learning models, then the deployment of those machine learning models, and then auto-scaling sort of graphs, real-time graphs, and finally the monitoring. And those will interact with all the other tools that you're familiar with, like IDEs and notebooks and sort of AutoML frameworks and CI and Jenkins and so on, through APIs and SDKs. So that's essentially what we're trying to do. And now we're going to focus mainly on the real-time pipelines. Next, Sar. So what I'm going to show you is a couple of demos. The first one, which is the simplest one, is how we're building a pipeline for processing news articles. So we want to fetch news articles from some external source and then start transforming that piece of news and extract data, summarize the article, extract keywords, and so on. So in order to do that, we essentially want to build a set of transformation. We want to build a graph, and this graph will later on translate to a serverless function that executes that, and potentially even multiple serverless functions that this graph is distributed across, and just finally just writing to a database. This, by the way, this demo is also public. It's part of the MLRun demos Git repository. There is a link that you can see here, along with a few other demos that we can find there. So let me share my screen. Can you unshare?
Yep, we'll just pause there quickly for another poll while you're setting up the demo. Our second and final poll today is, what is your biggest challenge with NLP models? So please do let us know. And we'll give it 5 last seconds for anyone who wants to take part. Great, thank you very much.
Okay, so let me share my screen. Okay, you see my screen, my notebook?
Yes, we see it.
Great. So let's start with this this example. Again, we have this news articles that we want to feed through a set of transformations, and essentially this way process them, write the results into a database. So what we have is essentially all those transformations that we're going to use are in a Python file. This one. So we have a set of functions, regular Python functions that are going to be called and process different aspects of our document. And what we're doing here in our notebook, we're creating a function. In MLRun and Nucleo, everything you essentially is a microservice function, pretty much like Amazon Lambda, just faster and a lot more flexible. So what we want to do is create a function object from our code. So we essentially use a method called code to function, which takes our code and builds a microservice function. With that function object, we can also specify things like number of replicas, auto scaling policies, if we need GPUs, if we need a bunch of packages in this example built into our function. So we can describe our sort of infrastructure through code and through very simple Python classes. So first thing we did is we defined the function that contain our setter transformations.
There's a request here to make your screen bigger if possible, to make the demo a bit bigger.
Okay, let me try that. Okay, so the next thing that after we have the code, we want to build a graph. We want to build a set of transformation and how the code, how those classes or functions are essentially built into a pipeline, as you can see here. Now we can build way more complicated pipelines. I'll show some other examples in a second with branching and conditions and sort of parallel operations, etc. We'll stick these examples to something simple where we get an event. The event could arrive through Kafka, Kinesis, HTTP, whatever type of event source we'll choose in the configuration. And then it will just go through those steps. The way that we define the graph is just creating a topology, a flow topology, or a workflow topology. It's going to be asynchronous, so it's going to be parallel, high performance. And then we're just going to specify the different function handlers that we're going to use. Now, one of the nice things is that we also have a bunch of library classes that we can just use. Like, we want to write into a database. We don't want to write the logic of how to write asynchronously in parallel to a database. We just want to say, give me a step that does write to a NoSQL database. Here's the URL of my database, and that's it. And there are other operations like flat maps and sort of readers and writers from object store, from databases, from time series databases, and so on. So we can just build this transformation graph. And then the first thing we want to do is essentially simulate our graph to see that it's actually working. So the best way is to use our ID, our PyCharm, or our notebook to simulate the graph. So the only thing we need to do is essentially create a virtual server, or essentially a mock server, where we can just throw in requests into that virtual server. Just, here's like the URL, the body of the message that we want to feed into our pipeline, and then examine the results of that pipeline. So what this will do, it will actually build the entire pipeline in memory as a set of Python objects, and then we'll run through the pipeline and see that it's actually doing all the NLP processing. Now, at a certain point after we finish the debugging, and the nice thing here is that if we work like in PyCharm, we can put breakpoints, we can very easily debug our code. Once we feel everything is great, the only thing we need to do is say deploy. When we issue this command deploy, it builds the containers for us. It adds those packages we requested. It will allocate the infrastructure. If we requested GPUs or a certain factor of scaling, we'll do all of those things. And that will essentially generate a serverless function, which will auto scale based on our demand. So we stay in the plane of writing simple Python code, and all the instrumentation, all the work of building a fully managed service is done automatically for us. So this is this deploy. And then we could also play with the real service. When we choose invoke, it essentially uses the real HTTP endpoint and calls our live serving function. And we can see that it actually builds all of those results. And remember that we wrote everything to a database. So if we later on open the table in the database or use Grafana to visualize the table in the database, we see that all of those articles that we've indexed are essentially written to the database. If we want to go to see how it's actually managed in Nucleo, the serverless engine, so you can go to that project that we've defined, and we could see that serverless function in action. We could actually see the code that was there in our notebook. It was essentially pushed into the serverless function. And the function has lots of different configurations. We only set few of them, but a lot of configuration around scaling and credentials and other things. And the function can also have different types of triggers. Right now, we specified a simple HTTP trigger, but through the UI or SDK, we could choose any other trigger. Like if we want to listen on Kafka as an input, that will be done automatically for us. Now we can build way more sophisticated topologies. There are a few that are, if you go into the MLRun documentation to the section of serving and data pipeline, we're actually working on beefing up the documentation. You'll see all the how it's working, and there are different examples here. One which is sort of a serving function example where we see data pre-processing, data enrichment, ensembles across multiple models, post-processing, exception handling. So still, it's this entire topology was built using 10 lines of code in Python, and the code for it is again couple of dozen lines of code in general. So we build a production pipeline with pre-processing, model serving, etc. Using a few lines of code. We can test it. Once we see it's working, we choose deploy, and it builds the entire thing. There are other examples that you can find. This is more of a more advanced NLP pipeline that spans across multiple functions, because you may want to use GPUs, as Nick mentioned, which are going to be separate to a separate container. So here we can also see other example where we can break the code to multiple functions and build more advanced topologies that include queuing and breaking, again, this entire workload to multiple containers, but all logically are managed as one big real-time pipeline, where every step in the pipeline is essentially a composition, is essentially auto-scaling by itself. So each one can scale individually. So that's it from the demo. We can open it up to questions and.
Thanks, thanks, Yaron. Yeah, we do have some questions in the Q&A channel, so I'll go ahead and read those out. The first one is for Nick. How did you define schemas for the topics, and check if, for example, a pipeline composed of stages compiles with regard to their output schemas? I hope that's clear.
Yeah, absolutely, it is. So I think the key thing is that you need to have some form of a schema registry and use something that is, I would recommend something that's more strongly typed as a data type to sort of interchange between your steps. So as opposed to using JSON with absolutely, sort of free reign on whatever you want to put in there, I would recommend taking a little bit of time and discipline to using something like Apache Avro, which supports schema evolution as your way of sort of managing those critical interfaces between your functions. It's just one of those things that down the line you'll thank yourself for. And also Avro has the benefit of being a much more compact message as well. So you're not having to send keys every time, you're actually just really sending the values in byte form. So I hope that answers your question.
Thank you, Nick.
Mm-hmm.
And we got a comment here that yes, it does. So thanks for that. The next question is for Yaron. Is the dashboard open source or only a part of the Iguazio platform? So maybe we can talk a bit about the difference between the open source and the enterprise version.
Yeah, so both all the MLRun user interface and the Nucleo interface are open source. Some demos include Grafana, which is also an open source tool. So all those things are open. Where Iguazio platform stands is like, if you use the open source, you need to integrate all the components, including storage and security and single sign-on and load balancers and all of that. When you go to Iguazio, you essentially get something which is fully baked, working without the need for you to install Kubernetes and all the resources and verify everything is working. And you get enterprise functionality like user authentication, RBAC, logging, monitoring, etc. And there's also a built-in data layer, which is very high speed built into the Iguazio commercial product. It's very essential to move data around between those containers and for building those workflows.
Excellent. And there's also a question about the monitoring part, whether that's open source or enterprise. Maybe you can speak to that.
The monitoring is, you mean the model monitoring and graph monitoring. So it is part of the open source, but right now the integration around the data that's used, it's using a time series processing engine that is in the Iguazio commercial product. So part of the functionality for the real-time monitoring requires the Iguazio product. It is in the open source, it is pluggable, so you can essentially build, attach it to other types of databases, but that requires modification or extension of the open source.
Excellent. Thanks, Yohan. There was a comment here in the chat earlier about the fact that there are lots of complexities to building NLP pipelines and definitely to scaling them. So there's a question here, Nick, for you. What was the one thing that you found most challenging in the process?
That's a really great question. So I think at the end of the day, it comes down to sort of composition and also trying to line up your event windows as much as possible. So when you have a document that's being processed by different sets of processors and they're all sort of potentially working on different documents at different times, your streams can kind of start to diverge over time in terms of sort of what is at processing time available in the window. So that really comes into from like an engineering perspective, being able to go in and potentially use some windowing alignment, and that's where using a NoSQL store is really useful, possibly. So having a data layer built in is very helpful in that way. That's one of the largest challenges, and then I would also say trying to sort of isolate the different bits of compute as much as possible, getting incredibly granular with that, because again, if you're wasting minutes on millions of documents, that is a very costly. That's really costly. I wouldn't call it a mistake, but engineering challenge. So.
For sure. Our next question: do you plan to provide a view to some benchmarks with defined configurations? The main aim is to see that performance is stable or better with the new versions of MLRun. Yaron, do you want to take this one?
So with MLRun, think of it as more of an orchestrator, where the underlying processing engine, the underlying thing that runs, as Nick showed, is Nucleo, which is a real-time serverless engine. Nucleo is a sort of multi-threading. It has a very high parallel design. Within the Nucleo repository, there is a set of benchmarks that show the performance. So you can run those benchmarks and also compare them with other frameworks of your choice, and there are some numbers of it.
Great. Another question for Nick. For the initial training with all documents, how many documents are we talking here? I guess more or less. How long did it take to train and build the model? So what can you say to that, Nick?
Sure. So I guess I'll start with it's not just a model. So back to sort of that really complex pipeline, the example that I showed there. We're not just talking about one model. This is tens of potentially deep learning style models. It's not uncommon for us to actually use boosted trees in sort of certain scenarios. So what I can say maybe in like broad strokes is if we were to train maybe a very specialized classifier, right? So we've routed some documents down a path, and then we want to further refine what we're going to extract out of them. So we might need to say, do we think this document contains this type of, an entity or thing like that. That can be in terms of thousands or tens of thousands of documents at times. You don't necessarily need an enormous document set for something like that. And in fact, you might not be able to find an enormous document set for some of those more specialized edge cases. We have annotation teams here on staff that work very, very hard to provide us with really great training data. For other models, though, for deep learning style models, I mean, maybe it would be helpful to talk about sort of GPU hours in terms of like how long they would run for. You know, it could be 50 hours, 50 to 100 hours even to run for sort of a singular model. So again, being able to do parallel training there is very, very important. I hope that answers your question.
Thank you, Nick. We just have time for one last question. What's a typical time frame for developing the entire ML lifecycle, and what does the time spent on each step look like? I imagine that's quite a tricky question. It might depend a lot on the use case, but what can you both say on that?
I guess, so how I would think about it is in terms of iteration. So the first thing that you absolutely have to, that you want to do quickly and very efficiently is really refine what your problem is. So a lot of times we'll get asks that are pretty vague. So trying to get down to what are we actually trying to optimize for? What are we trying to predict? What is the business value there? Because that'll also restrict some of our options later down the line. From there, really getting into reading original research sometimes, if the problem is really complex, doing some sort of analysis around what kind of hardware we think we're going to need for both the training and the serving life cycle, depending on the approaches that we choose. You know, I mean, again, that part of the process can last a few weeks. If it's something where we need to do something totally net new, it could last a couple of months even. What we're trying to do really, though, is once we have a finalized sort of, you know, it's got all of the check marks from the business, it's got all of the check marks from peer review and all of that internally. How do we get that to production as quickly as possible? That's really the part of the life cycle that we're optimizing for, and trying to get that down into days and weeks. Whereas previously, that part of the process even could take many months. So,
Johan, is there anything you want to add to that?
No. Well, I just shared a couple of links where people ask where the demos are.
Oh, wonderful. Yeah, there were a couple of questions here about the demo code. So that's now in the chat. We do need to wrap up. So I will just share my screen quickly. And I promised to show the results of the poll. But before I do, I just wanted to share that we have a lot of MLOps resources available for you on our website. If you go to guasio.com/MLOps, you'll find previous sessions of this webinar series, blogs, videos, and other helpful resources where industry experts like Nick share their experience in operationalizing machine learning. So do feel free to check them out and let us know what you think. And with that, we'll take a look at the poll results. So we'll start with, where are you on your data science journey? And I hope that you can all see the results here. So 45% of you have models deployed in production, which I have to say is very rare. We rarely get this amount of people who have projects in production. So that's excellent and kudos. 32% are just learning about data science. 17% have a working model in the lab, and 6% have an AI use case, but no model yet. And we'll just take a quick look at the challenges with NLP. So regarding this question, 27% of you are not currently working on NLP models. So it's a good thing you joined this session before you got started. Hopefully you got some helpful tips here. 22% are training the model. 20% cost-effective scaling on the inference layer is their main challenge. 18% have a challenge of monitoring the pipeline. 9% with fast deployment, and 4% don't have any challenges. You guys are so lucky. Thanks very much for sharing that with us. That was very, very interesting. So with that, I would just like to thank Nick and Yaron so much for this deep dive into scaling NLP pipelines. And thank you everyone for joining. Do join us on our community. There were a few questions we didn't get to, so we'll be very happy to answer them on Slack. And please stay tuned for our next episode, which will come up right after the holidays. Thank you all so much.
Thank you, Sahar, for organizing. Thanks everyone for joining.